Okay, hello and welcome everybody to the first class on ME 201 Fluid Mechanics. We have already met on last Thursday. We had the meet and greet session on Teams. I hope you were there. If you were not there, we have recorded the video and it's available on the Teams group. So since we have already met, you already know me, but still, this being the first class, let me formally introduce myself again. So I am Alok Kumar and I am an assistant professor. So I've written my name here, but I've provided some of the other details as well. And I'm an assistant professor here in the Department of Mechanical Engineering at IISc. This course, ME 201, is offered by the Mechanical Engineering Department as a core course, and there will be two professors teaching this course this time. One of them is obviously me, and the other professor is Professor Ratnesh Shukla. So the first part I will cover, and then the second part of this course will be Professor Shukla will be taking over for that. Now, if you want to reach me, I have given all this information out earlier as well, but still there's no harm in revisiting that. My phone number here is given. This is with the area code. If you are dialing from inside IISc, then all you need to dial is the last 4 digits, 2958. This is my email here, alokkumar@iisc.ac.in. Now, don't make the mistake of sending an email only to alok@iisc.ac.in. There's one more professor, Alok Paul, in material science, and that email belongs to him. So it has happened on more than one occasion that there has been this confusion between that. So if you are using my email, use my full name. Okay. The course website, there is a slight update about that. What I have done now is that the course website is actually, it's very simple to remember. It's kumarlab.com/courses. And I have now made available both the HTTP and HTTPS, the secure site. So it should not matter whether you type HTTP or HTTPS when you are trying to link to the course website. And if you have any problems accessing this, let me know. I hope now that I've made it available in both the secure and the unsecure format, I don't think any of you will face any issues while connecting to my to the course website. All the homeworks, etc., will be listed here. They'll also be listed on the Teams website. So I think you'll have access to the information in multiple ways, right? Now, the textbook that I'm going to follow is, and we have already discussed this again last Thursday. This textbook is Fluid Mechanics by, there are 3 authors here, Piyush Kundu, Ira Cohen, and for the new edition, we have David Dowling as well as one of the authors. Now, this textbook is very nice in the sense that it gives a very good overview of the topic and covers some of the fundamentals as well as covers the advanced topics. So the way it usually goes is you have an introductory chapter here, and then the other chapters are the second chapter is on Cartesian tensors, then it's kinematics, then conservation laws, and vorticity dynamics and ideal flow. So what I'll try to do is I will try to get to the first, to the basically to the 6th chapter in my portion of the course, which will most likely end around end of November. So that's when my portion ends, and then Professor Shukla takes over and he takes you through the rest of the course. This is a suggested textbook, but that doesn't mean that I will be following this exactly. Now, this is a good textbook in the sense that I will be following the manner in which the material is laid out. So we will start with an introduction, and then we'll move on to tensors, vectors, etc. And then we'll move into kinematics, and then to the rest of the topics. But this doesn't mean that whatever is going to be taught in the class is going to adhere exactly to this book. Okay, so I urge you to follow the class pretty closely. There are other very good texts in fluid mechanics. There are many good texts actually. There's not enough time to sit and go through them. Some of them are, for example, there's a good textbook, and specifically if you are looking for viscous fluid flow, there's a textbook. This is my copy by Frank M. White. This is my copy which I bought when I was a PhD student, my beginning level graduate course. Then there's another book which is quite mathematical in nature. It's a very short small textbook, but covers quite a lot of material. And this is called A Mathematical Introduction to Fluid Mechanics by Corinne and Marsden. So there are many textbooks that one can go through. We will be giving you references to other textbooks whenever required. So at the moment, the textbook that we have discussed is good enough, and by which I mean this book. Now I have also provided on Thursday, I had provided you with a link which, if you are accessing it through the IISc academic LAN or the internet, you should be able to get access to the entire book via that link. So if you don't want to buy the physical copy, you also have access to the entire soft copy versus through the IISc LAN. If you have difficulties accessing the book, let me know, but I don't think you should have any problems. If you are situated outside of IISc, then obviously you are going to use the VPN to connect, right? Now for this course, obviously this is an interesting semester, because of course, I mean, this is the time when we are used to seeing you in the classrooms. We have a lot of new faces. This is the time most of us look forward to. This is when the campus is abuzz with all the new students who have come in, and it's a pretty exciting time. It's almost like a mela that goes on. But unfortunately, that's not going to be happening this time. So we have to do this class. At least this semester looks almost the entirety of it will be online, and that's something that both you and me, we have to get used to. So we should set some of the ground rules right away. One of the ground rules is that I will not be providing written notes for this course, and although I will be using a combination of Blackboard teaching and an app-based way of communicating with you. So some of the lectures I'll record like this, which is just a video recording directly on a Blackboard, on a whiteboard here, and the other, for some of the other sections, I might just use an app-based system to record, and then you'll not see me. All you will see is an empty is a screen where I'll be just writing. So that's how we have to do this course, and that's why it's important for you to know that since I'll not be providing notes, you should take class notes while going through the lecture, and that's going to be quite important. So do not miss that, because otherwise at the end of everything, if you're just browsing through the lectures and not taking notes, you might be in a problem. Okay, so hopefully that is clear. So don't, after a month, don't start requesting me for notes of this class, etc. We are already providing you with recorded lectures, and that's already quite a bit of work for us, by the way. Okay, so that is clear. What is, just a second, let me see. Right. So our classes are scheduled Tuesdays and Thursdays, 8:30 to 10 a.m. Right? That's the slot that has been given to us. Obviously, as far as classes go, the slot is not very important. So what we will do is, I will be recording lectures for, let's say, it's a 1.5 hour class. For that 1.5 hour class, I'll record lectures of about 1 hour, and I'll post them before the class. Okay. So for the Tuesday class, for example, the lectures will be posted before that. So the classes are, and then what? So what do we do during the actual class time? Well, we will not be using the actual class time to the full extent. What I'll do instead is that from 9:30 to 10, I will come online. I've already set up on Teams, I've set up a discussion time, which is 9:30 to 10 every Tuesday and Thursday. And I'll come online and we can have a face-to-face discussion on any questions you might have, the preceding lectures. Okay, so do go through the lectures and do come online if you have doubts, you have clarifications, because one of the issues with this kind of teaching is I have very little idea of what you guys are going through, right? And whether or not you are getting all the concepts that I'm trying to explain are getting through. So it's very important that you give me feedback during that time, and please don't hesitate in giving feedback. It's also very important for me to understand whether you are getting what I'm trying to say, and I might have to make corrections while doing that. One of the reasons I'm doing this video lecture like this in front of a blackboard is because I believe the last semester some of the courses that I taught where nobody was able to see me and it was just an app-based writing, I felt that there was a slight disconnect between the teaching and the student. So if I were there, believe me, even I would be bored. There's somebody writing and it's just a disembodied voice talking and there's something getting scribbled on the screen. So I think that's why it's important for us to have discussions. So do make use of that. Okay, let me see. Is there anything else? Okay, so I think, yeah, that covers more or less it. So let's get on with our class material for today. Okay, so this is a fluid mechanics class, and what is the most obvious question you can ask at the beginning, the very first lecture of a fluid mechanics class? I think the most simple question you could ask is, what is a fluid? But that's not an easy question. The question is obviously very simple, but it's not that easy to answer, and we'll see that. But before we go to asking ourselves what exactly is a fluid, we will discuss what is the continuum hypothesis. Now, the thing is, there are many ways of teaching this kind of topics, and we know that in reality, matter is made up of molecules. So, be it solid, be it fluid, or be it gas. Be it liquid, be it solid, or be it gas, you should be able to understand it from a first principles molecular perspective. That's easier said than done, but that is an entire field of statistical mechanics and, let's say, condensed matter physics and kinetic theory, where we do tend to look at matter from the molecular perspective, and we do try to understand its behavior from that. Now, that is a statistical mechanics approach, and we will not be using that in the class. Why will we not be using that? Well, we will not be using that because most of this course material can be approached from the perspective of what is known as the continuum hypothesis. What is the continuum hypothesis? Well, it's there in the book also, but if you want to state it very simply, continuum hypothesis is that you can apply the matter is continuous enough that you can apply the tools of calculus that you have learned till now straight away to that matter. Okay, so something like a fluid or something like a solid is it's in itself, although it is composed at the small scale with molecules, etc., you can neglect that and you can treat the entire material as if it was continuous. And you can just straight away start borrowing all the tools of calculus that you have already been exposed to, and straight on go ahead and apply that. But we must, so it does appear when we look at matter, when we look at, let's say, I have this bottle of water here, right? There are no molecules to discern. It just looks nice and continuous, right? And that basically means that the molecular length scale is so small compared to some of our problems and issues that we are dealing with, that we do not need to bother with it. But this is a very qualitative way of telling you this, right? So can we make this a little bit more quantitative? Well, yes, we can. And the way you would do it is we'd use something called the Knudsen number, often denoted by Kn. And this is usually defined as some microscopic length scale, or whatever is the microscopic operative length scale, divided by the macroscopic length scale. What is this microscopic length scale we are talking about? Well, for example, if you are discussing a fluid and we know that matter is composed of molecules, then these materials are interacting with each other, and there is some empty space in between these interacting molecules, right? But molecules are always in motion. So this empty space can be characterized by the mean free path of the system. So this microscopic length scale can be thought of in this particular case is your mean free path between molecules, and L is some system length scale. Okay. So Knudsen number is nothing but a ratio of two length scales, okay, lambda divided by L. So this is a non-dimensional number. If you have a gas, can we estimate what this mean free path is? Well, let's say if you want to do a quick calculation, okay, so quick and dirty estimate for lambda. You know that the gas relationship says PV equal to nRT, right? So if you have 1 mole of gas, then what is the approximate volume? You can calculate from this equation very easily what is the volume it occupies at standard room temperature and pressure, right? So you will find that this volume is volume of 1 mole is around 22 liters, or 22 into 3 centimeter cube. And how many molecules are there in this volume? Well, we just said 1 mole, right? So we know that the number of molecules are, so in this volume you have 6023 into the 23 number of molecules occupy this space. Isn't it? So how many molecules are there in a unit volume? So if you want to calculate that quantity, let's say that's gamma, then that quantity is this 6.023 into 10 to the power 23 divided by this 22 into 10 to the power 3 centimeter cube. So if you do this quick calculation, and what your answer will come out to be, I've already done it and I've kept it with myself, it comes out to be 2.7 into 10 to the power 19 centimeter cube inverse. Right? Rather straightforward. I mean, you can just quickly check my calculations. I mean, I might be wrong. If I am, please let me know. So this is basically the number of molecules per unit volume. Okay. Now, if you want to estimate lambda, let's say the cross-sectional area of a gas molecule, let's say oxygen, nitrogen, or something like that, that you can easily estimate from molecular sizes. That will probably come to around 10 to the minus 15 centimeter square. So the mean free path here, this lambda that we were talking about. So this, okay, I'm running out of space. Okay, so I'll just say, so this lambda will be approximately the inverse of this gamma into A. So now we have numbers for both of them. So please do this calculation, and what you should come out with is a number of the which is probably less than a micron. So this is in the mean free path of a molecule for a gaseous system is of the order of less than a micron. So you can imagine that for liquid systems, so for example, for this water here that I have, the mean free path must be much smaller than this, right? So now in this particular system, if your system length here, which is the important quantity, so can I erase this? So I think you have taken care of this. So let me just go ahead and erase this part. I mean, the advantage of YouTube is you can obviously pause and make sure you have the notes. So if you're in your general flows, let's say this is of the order of 10 to the minus 6 meters, and your flow length scale is of the order of 1 meter. Let's say there is a particular case where you're looking at flow over something large, then your Knudsen number is very small, right? And this is much less than 1. So if your Knudsen number is really much smaller than 1, then your continuum assumption is valid, and you can just neglect the entire structural constituents of matter and instead just behave as if it is as continuous as space and just go on with your calculations. Obviously, when Knudsen number starts becoming of the order of 1, that is when you need to start taking care of the real of the molecular nature of matter. When can that happen? Well, if you have, for example, gaseous flows through nanochannels, then you might have to worry about the lack of continuum nature of matter, and then the tools that we are going to develop in this class will not be useful for you that much. And then you must take into account some of the other tools which may be from statistical mechanics or condensed matter physics, etc. So those would be dealt with in more advanced courses, but not here. For us, now that we have talked about Knudsen number, we'll never talk about it in the rest of the class, because the entirety of this class will always have Knudsen number much less than 1. Okay. The other interesting thing, there are two more things that I want to specify. One is, see, you will find when we do fluid mechanics and we start looking at many of these different problems, we'll see that we will come often across non-dimensional numbers. So non-dimensional numbers is going to be sort of a bread and butter for many of the fluid mechanical problems. So in the class of non-dimensional numbers, in fluid mechanics, they are almost all generated under by ratios of non-dimensional numbers in fluid mechanics are generated by taking ratios of two quantities. And what are those two quantities? Well, the two quantities can be, for example, if you have Reynolds number, okay, and we'll come to that later. So something like Reynolds number, capillary number, it's just number. So this is usually denoted by RE, capillary number is denoted by CA. These are ratio of forces. Okay. And Knudsen number is an example. Where this is a ratio of length scales. There will be other numbers such as Deborah number and even Peckley number. This is denoted by DE, this will be by PE. And these are, you will see that these are ratios of time scales. You will also have numbers like Mach number, which are a ratio of two velocity scales. So non-dimensional numbers are something that are very common. So I hope through Knudsen number you have gotten some idea of the various of the general format for non-dimensional numbers that we generate in fluid mechanics, and they are ratios of two things. And we'll see how some of these other numbers come up. We'll not obviously encounter all of them during the course, but we'll encounter some of them. But fluid mechanics abounds in these non-dimensional numbers, especially if you start taking mass transfer, heat transfer into account, you will come across many of these non-dimensional numbers. And they help us to make some important judgment calls when it comes to very complicated problems. And that's very important. So for example, we saw here that the Knudsen number, if it is much lesser than 1, then we can safely use the continuum hypothesis. The one more thing here is that, see, I have not given you, see, the relevance of these non-dimensional numbers is to provide you with a tool, a quantitative method to make a certain judgment, okay. And here it is not, this is not necessarily a very precise number. It doesn't have to go into 10 decimal places when you are writing it. The order is what is usually most important, unless you are near some very critical value, but it's mostly the order which is very important. So we do not specify these numbers down to many decimal places. And the idea here is that these are approximate number orders of magnitude values that are relevant to the problem. Okay, so don't try to write this 10 to the minus 6 meter, 10 to the minus 6 as 0.0000 something, some decimal. That's not how you represent it. Okay, so we have had our introduction to the non-dimensional number, especially to Knudsen number, and we will be using the continuum approach throughout this course. Okay, so that part is settled. Okay, so that brings us to the very simple question, which is, what is a fluid? Very, very simplistically, the answer to that is anything that flows is a fluid. What does it mean, anything that flows? Well, let's say if this is water, if I were to pour it down, this water is going to flow out. But this flow is not the same as, let's say, if I were to take my phone here and drop it. The two are not the same things. Why? Because when I drop my phone, that is going to follow more or less a rigid body motion and just fall under the action of gravity. But when I'm tilting this and pouring this out, this entire fluid body is deforming in structure, and different elements will be flowing at different or moving at different speeds at different time, which does not happen with my phone. When I let it fall under gravity, all of it is moving at the same velocity, it's shared, but not so in the case of this fluid. So in a sense, this is a fluid because it is going to flow. Most books will introduce you to this idea of shear. So it will say that a fluid is something that does not sustain shear, so you apply a shear force and then it will start to flow. But they miss out on one important thing, which is flow between what? So for example, when I tilt this bottle, my water will flow out immediately. But what if I had butter inside? Will that flow also? It will flow, but it will flow slower at a slightly retarded time scale, but it will surely flow. And if you have, for example, jam, and you can do this experiment at home, by the way. You can keep some butter or jam on an incline, and it will not obviously flow down nicely like a fluid, like water immediately, but just go and come back after an hour or a couple of hours and you will see that it has moved, right? So even that jam is flowing. We know that glaciers flow. Obviously they flow very, very slowly, but even the flow, right? So one of the assumptions or the inherent background when people talk about fluids is, in what time scale are you expecting things to flow? And if you do not specify that, then that question of what is a fluid is not really well posed. So you have to tell me, excuse me, sorry, you have to tell me is what is this time scale of your experiment, right? Do you have 1 million years to wait? If you do, then well, many things will flow, right? We know that the Himalayas are still rising at a small, very, very small speed. So maybe if you have 1 million years, the Himalayas would have flown up a little bit, or maybe even flown down. I don't know how the geophysics of that will work in 1 million years, but there will be some motion. And not all of it will be rigid body motion. So unless somebody gives you a good idea of time scales involved, and you must have a clock, you must have a watch. So when you're doing this experiment, when you're asking this fluid mechanics, this question is what is a fluid, you must have a watch, and where you have this time scale of your experiment, you must tell me what is the time scale that I need to worry about. And without that, this question is not well posed. So what I'm going to do is, we are going to take this and I'm going to record the next video, but I'll do that in the app mode, and I'll introduce you, I'll take you, I'll answer this question in a slightly longish manner, where I introduce you to some historical ideas of time scales, and then we'll come to appreciate what is a fluid in some sense a little bit more. Okay, so I'm going to stop this video recording right now, and I'll catch up with you in just the next lecture. Okay.